I read somewhere that mathematicians can turn a sphere inside out.
Yes, that's true.
What's the big deal? Just poke a hole in it and pull it through.
Sure, but the point is to do it without making a hole.
But then it seems impossible.
You're right. You cannot do it with an ordinary sphere, like a basketball. You have to understand the rules of the game. This sphere is made of an abstract elastic material that can stretch and bend and pass through itself. But you cannot rip or puncture this material without destroying it, and you cannot crease it or bend it sharply.
If the surface can pass through itself, what's the problem?
Do you think allowing self-intersections makes it easy? Try it.
I'll push the two halves right through each other.
Be careful. What about that ring around the equator? Remember, you mustn't tear or crease it.
Let me try again.
That's no good either. You're pinching it infinitely tight.
But then there's no way. It's impossible. You'd have to crease or pinch it to turn it inside out.
It is surprising, but watch this.
Is this it? Is this a sphere turning inside out?
You bet. That wasn't easy to follow, was it? To figure out what's going on, let's look at something simpler. A circle. We'll build a vertical wall along the circle so that we can color the two sides differently. Can you gradually turn this circle into this other circle, where the purple and gold sides are reversed without creating sharp corners?
Of course. I can turn a rubber band inside out.
Remember, we're really trying to turn the circle inside out. We only built the wall so we could see the different sides.
Oh, yes. The wall has to stay vertical, and it can't have creases, but it can pass through itself. Fine. Let me try.
Watch out. That was a sharp bend. If we could make sharp bends in the material, we'd be able to turn any curve into any other by moving each point of the initial curve in a straight line toward a target point in the final curve.
But I can avoid corners altogether by making a loop smaller and smaller.
That's an interesting idea, but pulling a loop tight is not really a gradual change. It's like having a corner in disguise. So it's against the rules.
Well, if you can't have corners, and you can't pull loops tight, I think it's impossible to turn the circle inside out.
Yes, you're right.
Wait a minute. Am I supposed to believe that you can turn a sphere inside out, but not a circle?
Yes. There is something fundamental about curves that would have to change if you were to turn a circle inside out, and that something cannot change under our allowed motions.
And what's that?
I'll explain. Imagine a monorail atop the wall. Now, the rule about monorail traffic is that the car only travels forward, and it always keeps the purple wall on its right. We'll use a diagram to monitor the car's direction. On this track, the car is always turning left. As it goes around the circle once, it makes one full turn toward the left. On a more complicated track, the car might sometimes be turning left and sometimes right. But the net amount of turning after one complete circuit is always some number of full turns in one direction or the other. The number of full turns it makes toward the left is called the curve's turning number. For a curve where there is more turning toward the right than toward the left, the turning number is negative.
Hey, and if there's no net turning, the turning number is 0.
Right.
I had a hard time following the net turning for this winding track.
That's natural, but there's another way to get the right answer. Find the spots where you're traveling in a particular direction, like due east.
Let's see. Since we're looking from the south, that would be wherever the monorail is going toward our right, where we see the purple wall face on.
Exactly. At some of these points, the track is curving away from us. Viewed from here, it looks like a smile. At these places, the car would be turning left. At others, the track looks like a frown. Curving toward us, at these points, the car would be turning right. The net number of full turns increases when the car passes a smile and decreases when it passes a frown. Starting at 0. 1, 2, 3, 4, 3, 2, and we finish with 3. The turning number is the number of smiles minus the number of frowns.
I see. The turning number measures happiness.
If you insist. Now, the nice thing about the turning number is that it remains the same when a curve changes according to our rules. Frowns and smiles can appear or disappear, but only in pairs that balance out. The number of smiles minus the number of frowns never changes.
So a curve can only turn into another curve with the same turning number.
Right. The turning number is the fundamental property I mentioned before. Now, what's the turning number for the two circles?
This one has 1 smile and no frowns, so the turning number is 1. And if the gold is outside, 1 frown and no smiles, minus 1. It makes sense. On one curve, you're turning left all the time. On the other, it's the opposite.
Good. So the reason you cannot turn a circle inside out
is that would change the turning number. But wait, doesn't the same argument prove that you can't turn a sphere inside out? This sphere has a 3-dimensional smile, and this one has a 3-dimensional frown. So they have different turning numbers.
Not quite. Your analogy is good, but to make it complete, we must look at a general surface and consider all the points where it is horizontal and gold is on top. We'll draw horizontal stripes to make these points easier to locate. Smiles are like bowls, curving up. Frowns are like domes, curving down. But there are other points where the surface is horizontal that are neither bowls nor domes. They are saddles and look like smiles from one direction and frowns from another. Near a bowl or a dome, the horizontal stripes form rings. Near a saddle, they form an X.
But how does that change anything? Spheres don't have saddles.
Ah, but the point is how these features interact. Look, a dome and a saddle can come together and cancel out. Likewise, a bowl and a saddle can cancel out. But bowls and domes, like electrical charges of the same sign, normally don't get near each other. The unchanging number for surfaces, then, is this. Add domes and bowls and subtract saddles. This number is 1 for the sphere no matter which face is out.
Okay. I'm willing to believe that turning numbers don't prevent the sphere from turning inside out as they do the circle, but that doesn't mean you can actually do it.
We'll get to that. I know it's hard to see. Steve Smale proved it was possible in theory in 1957, but it took 7 years before Arnold Shapiro found a practical way to do it. Since the problem remained hard to visualize, more methods were invented later by Bernard Morin and several others. I'll show you Bill Thurston's method, invented in 1974. Let's go back to curves for a bit. Remember that this circle can only be changed into curves of turning number 1.
Still not allowing sharp corners, right?